we're going to start looking at oscillations. This is A-Level CIE Physics, whereby we're going to look at what are the main areas that you need to understand as far as A-Level Physics oscillation is concerned. If you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload another tutorial, you'll be notified. And also, if you have not joined our Patreon page, consider joining so that when I'll be uploading, you can be able to check the link in the description, guys, so that you can be able to access the PDF of these notes that I'm having at this given point. Now, in this topic, oscillations, basically you need to understand a few things that happens when an oscillation basically occurs. What is an oscillation in the first place? Huh? Oscillation is a repetitive motion back and forth, which can be observed when you talk of maybe a child or a kid or a baby, a child swinging in a swing. Or we can also talk of a mass hanging on a spring, moving up and down, displaying a repetitive motion. And basically that is what we talk about when we are talking about oscillation. So an oscillation must be repetitive. It occurs in regular intervals. We can talk of vibrating guitar. We can talk of a child swinging on a playground. Yeah, so those are some of the examples we can talk about. You can see here we have a spring which is moving up and down, and then we have a mass attached to it. Then we have a pendulum that is swinging back and forth. So if this pendulum moves from this point to this point C and then comes back, that's now a complete oscillation. If we have a trolley that is held by two springs on either side, so meaning if you are going to displace this trolley a little bit, it means you are going to have the trolley moving back and forth, and that is going to display what we call simple harmonic motion. So oscillations can be termed to be in simple harmonic motion, especially if there's no force that is going to reduce that motion. Because if you are having an object swinging freely like that, it displays simple harmonic motion. But if there is losing of force or energy is being lost, then we can have the aspect of damping motion, right? But also, if force is induced in an object that is oscillating, then we're going to have resonance. And those are the kind of aspects that we're going to be mentioning in this tutorial. So in this topic, you need to understand that when we are talking about oscillations, they can be described in terms of displacement, whereby displacement is the maximum distance from the point of equilibrium or the mean position. So for instance, if you are talking of displacing this from the mean position here, if you move it at a given distance, we are displacing it. Then amplitude is the maximum displacement from the mean position, and then we have period. Period determines how long a particle or an object takes to make one complete oscillation. Then when we are talking about frequency, is the number of oscillation made per second. Then in A-Level Physics, you need to understand the relationship between frequency and time period, whereby frequency is 1/t and periodic time is 1/f. So those are the areas that you need to understand. Then we have angular frequency. Remember, this omega we used when we were talking about circular motion. Basically, we was calling this angular speed. But when we are talking about oscillations, we shall call it angular frequency. And angular frequency is going to be given by 2 pi over the time period, or it can be given by 2 pi f, and this is given in radians. So if you look at this wave that we are having here, this one has a higher frequency than this one because it's making more turns. Suppose the time here is the same, then this has a higher frequency than the other one. So you need also to understand the concept of phase difference, and phase difference will be the distance between two similar points of wavelength times 2 pi or 360, or t, time taken between two similar objects in a wave over the time period of the one of the wave times 2 pi, and that's going to give us the phase difference. So those are the areas that you need to know when you are describing an oscillation or an object that is displaying oscillations. Now, you need to understand the term symbol harmonic motion. You need to know how to define the term symbol harmonic motion. I'm telling you that because that is a very, very common question that is usually asked. You can see here, this is one of the questions that was asked. State what is meant by symbol harmonic motion. And you're going to say symbol harmonic motion is a type of motion where acceleration and displacement are proportional and they act in opposite direction. So that is the definition that you ought to know, because you'll find that mostly you'll be asked to define the term symbol harmonic motion. You can see it here. It's being asked. Yeah, symbol harmonic motion. What resonance? We are going to look at that. So, and if you want to access this PDF that I'm having here, you can be able to access it in our Patreon page. A link in the description so that you can be able to download it, and then you get also the booklet, this booklet, so that you can work it on it. You can be able to answer. You can be able to answer questions on this topic. You can see there are many questions here from different years. Yeah, you can be able to access that together with the marking scheme. Just check our Patreon page so that you can be able to really access these PDFs that I'm having here. So if you had not also accessed the other one, yeah, so you can also check in the description there so that you can also access this one. Did you you can be able to access this one. Yeah, so there is another tutorial we had done before. Yeah, so that's, yeah, there's another tutorial we had done before on thermodynamics, and we answered this kind of question. You can be able to access them in the Patreon page. Okay. Yeah, so that you can be able to access that. Now, the formula that can be used to calculate acceleration in simple harmonic motion is A is equals to negative omega squared x, whereby this is acceleration is directly proportional to displacement. Meaning, if you displace an object, for instance, when we are talking about this object, if you displace it more, it's going to accelerate back at a higher acceleration. If the displacement is higher, then the acceleration also be higher, but it will be acting in the opposite direction. So that's why you can see we are having the negative sign here. The negative sign means that acceleration and displacement, they are always acting in opposite direction. So which means that if you have a graph of displacement, acceleration against displacement, then it means we are going to have a straight line that passes through the origin, because they are directly proportional, acceleration and displacement are directly proportional, then but the gradient of this line is going to be negative because they are always acting in the opposite direction. And if you want to work out maybe if a question is expecting you to work out the angular frequency, you need to find the gradient of this line, and you say gradient is equals to negative, because this gradient is going to be negative. Then we are going also to say negative of this gradient is equals to negative of omega squared. So negative and negative will cancel out with this negative here. The negative of the gradient and the negative of this omega will cancel out. Then you can be able to find the square root of omega, so that you can be able to have the angular frequency. Now, if you have the angular frequency from the gradient, they can go ahead and ask you maybe the periodic time or the frequency of that particular oscillation. So basically, you can be able to do that because you have to relay this formula that we have at this given point. Now, once we have identified that, another concept that you need to know in this particular topic is how to find displacement in simple harmonic motion. If the initial condition is that the displacement or the wave or this oscillation start from 0, you are going to use x is equals to x naught sine omega t, where x is the displacement, but x naught is the amplitude of this particular oscillation. But if the oscillation at time t equals to 0, it has some displacement, then it means you are going to use the cosine formula, which is x naught cos omega t. Omega is the angular frequency, right? So in the event you are calculating velocity in simple harmonic motion, you are going to use v is equals to v naught cos omega t. But if you are not having time, then it means you are going to be using this other equation which relates displacement, where v is equals to plus or minus omega, which is the angular frequency, square root of amplitude minus the displacement. Yeah. In the event you are going to be given equations like this, you'll be given a graph, in the event you are going to be given a graph that looks like this here, it means from 0 to x naught here is the amplitude, and this value above here is going to give you the maximum speed or the maximum velocity of the particle in this simple harmonic motion. Let's see, has there ever been a question like that? Yes, you can see here. Now suppose they are going to ask you to determine the amplitude. You are going to check what value is here. You are going to check which reading is at this given point and which reading is at this given point. Then you subtract these values, or you can be able to check this reading. You locate the midpoint of this, then you can be able to check now what is this distance from there, and that is going to give you the amplitude. And also, if you want to determine the maximum speed, you are going to check the middle point of this, and then you're going to check from here to here what is the maximum speed. Yeah, then you can be able to read it like that. So which means that this point here is going to give you the amplitude, and the reading at this point here is going to give you the maximum velocity of this particular wave. Maximum speed is given by this particular formula, and of course we know at maximum speed is when the object is moving at the equilibrium position. Yeah, so that's why we are arriving at this particular kind of formula. V naught is equals to omega x naught, where x naught is the amplitude of this particular wave that we are talking about. And also the relationship that connects the amplitude and the maximum speed maximum speed is 2 pi f x naught, where we can say that the maximum speed depends on amplitude and the frequency of that object that is moving in simple harmonic motion. All right, now as if that's not enough, we are going to look at energy of objects which are moving in simple harmonic motion. So you realize that if we are talking about a pendulum that is moving and oscillating within this particular plane, moving like that, it means at this point it will going to have maximum potential energy and the kinetic energy will be 0, and here is going to have maximum potential energy and the kinetic energy will be 0. So as this pendulum is moving from this point, swinging like that, at this point here kinetic energy is 0, so kinetic energy will be increasing and it will be having maximum kinetic down here. So as kinetic energy is increasing, as kinetic energy increases, potential energy is going to be decreasing, you can see. So we can be able to display the kinetic and potential energy on a graph as shown here. So as potential energy decreases, kinetic energy will be increasing, right? Also, energy of objects moving in simple harmonic motion can also be represented shown here. So this line at the top here is going to represent the maximum total, or the total energy. Yeah, the total energy is going to be represented by this line, using that line. So which means that this point here, if we were reading that from a graph that is plotted, then we can be able to read the total energy of the system at this given point. Then as the potential energy decreases, kinetic energy will be increasing. So potential energy will be 0 at the lowest point. At the lowest point, potential energy will be 0, but kinetic energy at this particular point will be maximum. So that is exactly what's being displayed at this given point. So as this object moves from this point, is proceeding to the other end, it means now the height will start increasing, guys. So meaning that as the height is increasing, then the potential energy will be increasing. So as the height is increasing at this point, the potential energy here will be increasing. Then when the height is increasing, the speed of this object will be decreasing, right? So the kinetic energy also will be decreasing because the speed of this object will be decreasing as it's approaching this end, and finally when it reaches here, the kinetic energy will be 0 at this point, but the potential energy must have risen up to that particular point. So you have to understand the energy transfers which are taking place, that is kinetic energy and potential energy, as far as simple harmonic motion is concerned. So we can be able to say that, so at maximum speed v naught, the maximum there is the maximum kinetic energy E. So we can be able to say that the energy is going to be given by a half mv squared naught, right? But we know from the other section we had said that v naught is equivalent to wx naught. So meaning v naught can be replaced with wx naught here, which we are going to replace at this given point here, and then we shall square. If you square this omega x naught, we are going to have omega squared x naught squared. So that means the total energy in an oscillation where we have simple harmonic motion can be given by the formula a half times the mass of the object that is oscillating times the angular frequency squared times the amplitude squared of that particular object, right? So basically that is what we are going to talk about at that given point. And here we are given a question that was tested in one of the years. So you are supposed to respond to it. You are asked what does this line represent, which energy is represented here, which energy is represented here and which energy is represented here. Something that we have really, guys, talked about. So you can see these are just questions that are mostly asked in your exam, guys. So you have to take this very serious, because in the next tutorial I'll be working out, I'll be discussing questions in this alpha booklet of simple harmonic motion. And if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload another tutorial, you'll be notified. And if you have not joined our Patreon page, please just join so that you can be able to access exclusive videos and also the PDF of the papers I usually display in my channel. Yeah, so the next area that we're going to talk about is damped motion. Damped motion, quite interesting. And this usually happens because, especially when we are talking about a system, yeah, an oscillation, right? So which means that in an oscillation there will be external forces. There are different external forces which are usually occurring or happening, or really happening in a system. We have air resistance, we have friction, guys, happening. So that means that the system will be losing energy due to that. So if a system is losing energy, and remember, energy is proportional to the energy of a system is proportional to the amplitude. Yeah, we talked about that in AS physics. So meaning that if a system is losing energy, the amplitude is going to be affected. The amplitude is going to be less, or the amplitude is going to be smaller. Now, for that reason, we are going to say that in this particular system, we are going to have a gradual decrease of the amplitude of the wave, and eventually the wave will have zero, or the amplitude is going to be very small to be detected. So in damped oscillations, the resistive forces such as friction and air resistance are the one that is going to lead to a result to the loss of energy from the system. And at that point, you need to understand that this damped motion is applicable in many areas, but we have different types of damping. We have critical damping, which result to an object attaining equilibrium within a very short period of time. It's going to oscillate within a very short period of time, and then it attains equilibrium. Then we have light damping. It's going to lose the amplitude gradually. And then we have now heavy damping or over damped, where an object is going to take a long period of time to come to equilibrium. And you need to understand that critical damping is applicable when we are talking about door locks, where you don't want an object to oscillate. Yeah, so you need, when you are just locking the door, the shutter immediately shuts. If it keeps on oscillating, the door will open again. So we don't want that. That's where we have critical damping applied. For heavy damping or over damped motion, that can be applicable in areas whereby we're talking about heavy trucks, which requires which means that once a truck has gone past a bump, it's not going to be oscillating up and down. And damped oscillation or damped motion is going to be also applied in cars, where we have spring, we have shocks in cars. So that's why it's going to be applied. Now, there's the concept of forced oscillation, because when we are talking about a system oscillating freely. There's no external force other than the initial force that was applied on that. But when we are talking about forced oscillation, meaning a driving force is being exerted into the system gradually or periodically. So for instance, if you are in a playground, then you have a swing, you keep on pushing a child or swinging, just keep on pushing. When the child reaches you, then you push. When the child is about to move to the other side, so meaning you'll be giving, or you'll be feeding in, you'll be giving in energy into the system. As the child comes, then you push the child, so the child will continue swinging, and then the amplitude will keep on increasing. So in this area, you need to understand forced oscillation as oscillation in which occur when there is an external periodic force which is being introduced in the system. Then the most important aspect that you need to remember is the concept of resonance. When do we say an object has attained resonance? What's resonance? You need to understand how to define the term resonance. And we're going to say that resonance is a phenomenon in which an object oscillates at maximum amplitude, and this happens when the frequency of the driving force matches the natural frequency of that particular object. And we need to understand that every object has got its natural frequency. Natural frequency is a frequency at which a system oscillates when there is no external force acting on it, right? So if the driving force has the frequency which is equivalent to the natural frequency of the system, it will mean that there will be maximum absorption of energy from the driving force into the system. Then meaning that the amplitude will keep on increasing in that process. So you need to understand that resonance is attained when the natural frequency, when the frequency of the driving force is equal to the natural frequency of the system. Yes, and damping ideally reduces the resonance frequency, and we need also to understand the applications of resonance. Resonance is applied in microwave cooking often, and also it's applicable in magnetic resonance imaging, which is MRI. Yeah, so under microwave cooking, remember microwaves have frequency and the water molecules in food have frequency. So what happens is that then the frequency of microwaves is equal to the natural frequency of water waves. So that when that happens, then it means that water waves will be vibrating at high amplitude, meaning now water molecules will have high kinetic energy. And when kinetic energy of water molecule increases, the temperature of water molecule increases. Then and that increases the temperature, and then food can be able to cook. Basically, that is how a microwave is cooking takes place. And magnetic resonance imaging and radio tuning circuitry is an application of resonance. Guys, we shall be working on this particular PDF in our next tutorial, now that we have discussed what these topics are about. See you guys in the next tutorial. Have a great day.